Let's talk about Newton's laws while I'm making a sketch of Nellie Newton, our physics mascot. Newton's three laws of motion are fundamental not only to physics, but to much of general science. These three laws have transformed the way we view nature. They were the first to convincingly show that nature follows rules. Newton's laws are three of these rules. First, some history. Some 2,000 years ago, before the time of Galileo, conventional wisdom held that a moving object needs a force to keep it moving. Things just don't move of themselves. Forces are needed. Galileo showed otherwise and maintained that in the absence of forces, moving things will continue moving. The tendency of things to resist changes in motion was what Galileo called inertia. Newton refined this idea and made it his first law of motion, appropriately called the law of inertia. Little Nellie Newton recites this first law.
Every object continues in a state of rest or of uniform speed in a straight line unless acted upon by a non-zero net force.
The key word is continues. An object continues to do whatever it's doing unless a force is exerted on it. A hockey puck at rest on the ice continues at rest if no force is exerted on it. Whack the puck and it will slide across the ice, pretty much at constant speed. So long as no force acts on it, the puck will continue moving in a straight line path. Newton's first law tells us what kinds of motion require explanation. Whereas the ancients believed that the motion of planets were natural, needing no explanation, Newton noted that the moon and planets move not in straight lines, but in curves, and did require an explanation. This led Newton to the universal law of gravity. We see that many things around us change their speeds and directions. Their motion is accelerated because they do encounter forces. What then? This brings us to Newton's second law, sometimes called the law of acceleration. Little Nellie Newton recites the second law.
The acceleration of an object is directly proportional to the net force acting on the object, is in the direction of the net force, and is inversely proportional to the mass of the object.
Which in symbolic notation is A is net force over m. With the appropriate units of acceleration, force, and mass, we can express this as the exact equation, A equals net force divided by m. A force is a push or a pull. Newton's second law gives force a more precise description by relating it to the acceleration it can produce. More often than not, we view acceleration as produced by a force. But can it be the other way around? That acceleration produces force? The answer depends upon the situation. Swing a bat against a baseball and the force of impact produces acceleration of the ball. Force clearly produces acceleration. But catch the ball and its rapid deceleration exerts a force on the player's glove. Acceleration in this case clearly produces force. Which produces which can be arbitrary. We often see Newton's second law expressed as F equals ma. Some students, including myself in past years, interpreted this to mean that force is a mass times acceleration. Not helpful. Instead, F equals ma should be read as the amount of force on a given mass relates to the acceleration produced by that force. For my taste, I prefer A is F over m. The examples that illustrate Newton's second law are endless. It's the primary law that first got humans to the moon. Newton's third law further illuminates the concept of force. Nellie Newton recites the third law.
Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first.
This third law is often paraphrased as, to every action there's an equal and opposite reaction. What it tells us is that forces always occur in pairs. Every force is part of an interaction between one thing and another. There's never only a single force in any situation. When you lean and push against a wall, you exert a force on the wall. You don't fall through the wall because the wall pushes back on you with the same amount of force. You push on wall, action. Wall pushes on you, reaction. Forces only exist in pairs, equal and opposite. Consider a cannonball fired from a cannon. Due to explosive gases inside the barrel, a force is exerted on the cannonball. Here's a snapshot of the ball inside the barrel. Its acceleration is enormous. A reaction force is exerted on the cannon, and it recoils, but with only a small acceleration. Although the forces are the same, the resultant accelerations are very different. This is because the masses are different. Yum! A rocket in space is propelled in a similar way. The rocket produces downward forces on exhaust gases. In doing so, the exhaust gases produce upward forces on the rocket, all the way to outer space. Newton's third law underlies the recoiling cannon and the recoiling rocket in all situations where forces produce changes in motion. It's all the same wonderful physics. More on applications of Newton's laws in other screencasts. I want to leave you with a question. Nellie's car accelerates along a road because its tires push backward on the road. That's the force acting on the road. Question: exactly what force propels Nellie's car forward? Identify this force. Until next time, good energy.